All right, the last item of our agenda for today is talk about combination circuits. And we're going to do that. I don't recall. That doesn't look like the right slide. Chapter 8, there we go. Okay, so a series circuit may be used to connect small voltages to obtain high voltages. High voltages may be reduced by connecting resistance in series. These are all the purposes or advantages of a series circuit. These are the drawbacks. Since the current is constant in a series circuit, we are forced to use only those devices which require the same current, and so on. Another advantage of parallel circuits: breaks should occur in any branch. Things will still happen, but maybe not the things we want to happen. As more devices are added, more current is drawn in a parallel circuit. That's one of the disadvantages. Parallel circuits are used when a constant voltage is required. Okay. If we combine series circuits with parallel circuits, we produce a combination circuit. Combination circuit makes it possible to obtain the different voltages of a series circuit and the different currents of a parallel circuit. So a parallel series circuit is one in which we have one or more groups of resistors in series and connected in parallel. And a series parallel circuit is one in which one or more groups of resistors in parallel are connected in series. That may sound like I'm saying the same thing, but it's not quite true. Okay. Now, this is the important slide. Steps towards solving a combination network. Number one, a group of resistors in simple combinations of two or more resistors which are arranged in either simple series or simple parallel circuits. You have to, in other words, identify what you're looking at. Are we looking at a parallel branch or a series branch? And how can we tell? Well, we're going to come to that in a second. Every group must be removed from the circuit as a unit and replaced by a single resistance which offers the identical resistance. The equivalent, in other words, an equivalent resistor. Whose theorem? Thevenin's theorem. Simplify, simplify, simplify. So, we redraw the circuit when we start simplifying. And we're going to redraw every time we simplify. I want you to remember that. Redraw at every simplification, because you're going to reuse that drawing when you come back. Because what we're going to do is we're going to simplify and go down. We're going to simplify and go down. We're going to simplify until we have one equivalent resistor which represents the whole circuit. That's Thevenin's theorem. Then we're going to start going back and figuring out what to put into each branch from what kind of circuit it is. Okay, redraw each simplification. And then solve the resulting simple circuit for all missing values. Go back to the original circuit or previous simplifications to find the voltage, current, and resistance for each resistance in the circuit. So what is that saying? Okay, then we go back to the previous simplification, go back until we solve the whole darn thing. Now let's have an example of a series parallel circuit. Here we have, not a great example, but this is a series parallel circuit. And R1 is 100 ohms, R2 is 250 ohms, and in parallel, they can be formed into a series, simple series resistors, right? Then below that, we have R3 and R4, and they're 350 and 200 ohms respectively, and we could solve those individually, right? Let's do that now. And we're going to look at R1 as what? What would it be? Let's go back to our first picture. If we have 100 and 250, let's use our TI-30X2S, and we're going to put in 100. Get your calculator out, hit clear twice, and put in 100, x minus 1 plus 250, x minus 1 is equal to, x minus 1 is equal to, and we get how many? 74.4. Let's say it's 74.4 for the moment. Now let's look at 350 and 200 in parallel. Hit clear twice now. Let's look at 350 and 200. So we're going to put in our calculator. Once we have it cleared, we're going to put in 350. x to the minus 1 plus 200 x to the minus 1 is equal to, x to the minus 1 is equal to, and what do we get? 127.2727272727. Okay, let's just call that 127.27 for the moment. Now we have resolved our two parallel branches and we only have two series. But is that simplified down to one resistor? No, it's not. Let's go to the next one. We now add those together and we get 201.67 ohm total. Is that correct? Now let's assume that we have, because we had that information in the very first slide, 24 volt total supply, right? So now we can find our current. Okay? So if we divide 24 by 201.67, we find that we have a 0.119 amp current flow in the total circuit. Is that correct? So now, knowing that our last simplification was a series branch, remember that? This one back here, that's series, isn't it? So what out of that simple series circuit are we going to plug back in? We're going to go back in and we're going to take the current, because the most common thing in series, or most important thing in series, is the current. So we're going to plug in the current here. And here we have our 0.119 amps and 0.119 amps in both places. And then if we multiply up, we should get our voltage drops. Is that right? So our voltage drops are 0.74 times 0.119 gives us what? Oh, we need to go look at our rules to make sure that we're going to do this correctly. We could look at our 3x5 card and we go, yeah, we're going to multiply up. And so we're going to find 8.85 volts on the top, and we're going to multiply up, and we're going to get 15.145 volts on the bottom. If we add those together, we have about the right voltage. So we know that our pure functional magic is still working. Is that correct? Now I want you to take a look at this. On the top, we have these totals right here. Now this R1, R2 is going to go back to being a parallel branch when we look at our previous simplification, right? And then down on the bottom, so what number are we going to take out of this into that parallel branch? Voltage. How about our bottom one? We know that R34 is a parallel branch, so what are we going to put back in that parallel branch? 15.145 volts. Okay, that's probably what we should go do. Let's go to this slide, and we plugged in our voltages, and it's a parallel branch on the top, right? And we have different current amounts. So if we go back to our 3x5 card for a moment, we can see that we're going to divide our 8.85 by 250 or 100. And on the left, we can see that's pretty simple. We're just going to move our decimal place to the left, right? Okay. So let's go down to the next slide. And we're going to find that our current is different in each of these parallel branches, because that's what parallel circuits do. They're current dividers. They have the same voltage, but they're current dividers. So we have 0.0885 amps in our left branch and 0.0354 in our right branch. If we add those back together, what do we find? We find our, wait a minute, wrong slide. What was our, wait a minute, wrong slide again. We're looking for our 0.119 total, right? Because that's our total branch. So if we look at this, we should be able to add 0.0885 and 0.0354, and that should come up close to our current, which was 0.119. Now let's go down and put our voltage in the bottom thing, and we're going to put in 15.145 volts. We're going to divide by 350 to get our current there. And on the right lower hand corner, we're going to put in 15.145. We're going to divide by 200 ohms. And because of that, we're going to find our current in each of those branches is 0.043 and 0.0757. And what do those add up to? Somebody say 0.119. I think it does too. Okay. Now, new problem. Now this is the other kind of problem. The first one was a simple, I've forgotten what kind of problem it was, but this is the other kind of problem. They're both combination, but the other one was parallel series or series parallel. This is the other one. So this is also a simple one. And we're going to look at, now look at this, and I want you to, now this is something you're going to start doing in the future. When you see a problem like that, you freak out, right? Oh no, I can't figure this out. Well, I goes, you guys would never do that, I know, but what we're going to do is we're going to draw a line on this. We're going to look at everything to the right of that, and we're going to see that there's only one path for the current flow to flow over here. So all of that is in series. And all of that is in parallel with this other path. So there's path 1 and there's path 2. So all of this series stuff on the right is one thing. So we can just add them up, right? So we know that we have 200, 400, and 600 ohms on the right. So we could add that up as a total, and that is 1200 ohms. So we're going to simplify that down to an equivalent single series resistor of E234, and 1200 ohms is that one. We also have an original 800 ohms, and we can now see that that's a parallel circuit that we simplified it down to, right? So now we want to simplify the parallel circuit with 800 and 1200 into a single simple series resistor. Now let's go back here and pull out our handy dandy TI-30X2S and hit clear twice and put in 800 x to the minus 1 plus 1200 x to the minus 1 is equal to, x to the minus 1 is equal to, and you should get, in my opinion, about 480 ohms, right? Everybody agree with 480? Okay, and we know from the first slide, nobody remembers that slide anymore by now, that we had 240 volts as our supply voltage. So now we have 2 out of 3 things, and we can divide. We look at our 3x5 card. We know that we're going to divide the voltage by the resistance to get our current. And 240 divided by 480, even a blind man can see that's going to be a simple answer of half an amp, 0.5. So we could get our power total by multiplying up. And if we went back to the next simplification back, we would go and take our parallel branch. We take our voltage because voltage is common in parallel. So we're going to plug in our 240 in both the branches, and we'll get a current in each one. And we'll get 300 milliamps in one and 200 milliamps in the other. Now we remember, I hope, that this was 3 different resistors all put together. So what information out of this are we going to take to that series branch that we had to begin with? We're going to take our current. Let's take our 200 milliamps back to our original 234 branch where it's all series, and we're going to plug in our 200 milliamps, and we're going to get 200 milliamps everywhere, and now we can multiply up to get our voltage drops, and not too surprisingly, we get voltage drops that add up. If we have, did I not have the right slide? There it is. We get 40 volts, 80 volts, and 120 volts. If we add those up, we get 240 volts. So our pure functional magic is working, and we've solved everything in that circuit. So that is combination circuit analysis. Now let's do one more. We'll add a slide, a blank one. I know it's hard looking at those blank slides. It's not going to allow me to add a slide, is it? Oh no! All right. Well, maybe we'll do that. No, we're going to do it here. Let me see. Let me hit pause for a second. I'm confused. Okay, now if we look at this, we can see that the obvious problem's right here. That we've got a parallel branch right in the middle of that. So we want to simplify that one down first, right? So we're going to take out our handy dandy TI-30X2S, and we're going to hit clear twice. We're going to put in 360 and x to the minus 1 plus 120 x to the minus 1 is equal to, x to the minus 1 is equal to, and we get 90. So let's go to our next drawing, which is non-existent, and we have, and that was R23, right? Is that right? Let me go back to this one and look at it again. 23, S23. Okay, R23 is 90 ohms. Okay, and then we had another one down below that, and it was 510 ohms. Let's plug that in, 510 ohms. And what are we going to do with that? We're going to look at that as one single series resistor, no problem, right? And this is R4, I forgot to put that in. So R2 through 4 is 600 ohms. Piece of cake, right? I think they've engineered this. And our original resistor, R1, was 1.2K. Oh, that's so slick. 1.2K, and 0.6K equals a series equivalent single resistor, which gives us ET. What was our ET? 16 volts. Okay, 16 volts. And we have IT, which we have no idea what it is just yet. And then we have 2,000 ohms total, right? Or 2K ohms. If we were answering a quiz question, we would put down 2K ohms, not 2,000 ohms. Do what? Oh, I'm sorry, 1,800 ohms. So that'd be a very wrong answer. Oh, darn you. 1.8K is the answer we would have on a quiz. Now it's not going to let me do anything until I... Yeah, these are, I'm sorry, they're in parallel. I'm sorry, I was thinking they were serious, but they're not. They're in parallel. Good point. So we're going to put in 1.2. Stop. We're going to put in 1200 x to the minus 1 plus 600 x to the minus 1 is equal to x to the minus 1, and we have a total resistance of 400. Better. 400 ohms. Okay, so now we have a simple problem of finding our total current, and we can see that 16 divided by 400 is going to be a very small number. Zero four something? All right, so we have 0.04 even, and that is 40 milliamps, right? So we can come back here into this parallel branch. Do we want to take into this parallel branch that was the last simplification here in red that we did before that? We had two parallel. What would we take into parallel? We would take the voltage. That's right. E1 is equal to 16 volts. And the voltage across that whole 234 branch was also 234, 16 volts. Okay. So first we would divide 16 by 1200. I1 we would find 0.01333333 and on. Okay, well that's a total for that one because it stands alone, right? But now we're going to go back to our total thing on the right that we started out with, and we've got 16 divided by 600, and we're going to have, what number is that? that right? 27 even? Yeah, 16 divided by 0 by 600. Oh, I've made a mistake. Okay, hold on. Okay, we find that if we divide 16 volts by 600 ohms, we find 0.026666 or 26.66 milliamps. And that is our total for the 2, 3, and 4 branch. And that simplification was a series simplification. So what are we going to plug into these? We're going to put in R23, not R, sorry. I23 is 0.02666. And down here we have, let's see, E4I4 is 0.0266 and on. So we find a current. Now, if we take this and multiply our 510 ohms by 0.0266666, we get our voltage drop, and that is the last thing we need to know about that one, right? And what do we get for that? So we multiply up on our R4, we'll get 13.6 volts, and that's the last thing we need to know about that, because this simplification right here is two different resistors in parallel. So when we go back to that simplification from the very beginning, we can see that we're going to plug in something from down here. What are we going to plug in from here? It's a parallel branch we're going back to, right? We need to know this voltage. So 90 ohms times 0.02666 is what voltage? Okay, so our total voltage is 2.399999 volts for our parallel branch. Let's take that back up here. We're going to plug in 2.399 and on, and 2.399 volts down here. And now, if we divide that voltage by 360 and 120, we'll find our currents in those two branches. Okay, so if we divide these voltages by the resistance, we'll get our current. So 2.399 volts divided by 0.01. Oh, wait, we already have our voltage and our current. We have everything we need. We've found everything, right? So we've resolved everything. And how did we do that? We broke it down, we simplified, and then we solved the totals. Then we've been back to the next simplification before that, and we plugged in the thing that is most important in that kind of a circuit. In series, we plug in the current. In parallel, when we're going back up, we want to plug in the voltage. And that's as hard as a parallel problem is going to get. But let's do one more just in case. All right, we have this fairly complex looking problem, which is really not that hard, because we can see that the first simplification is we're just going to cut this thing off. Whoops. And everything to the right of here is one equivalent series resistor, right? You can see that we're going to take this one and this one, and we're going to put it together, right? And we're going to put that, oh, wait a minute. Let me hit pause for a second. I've got to move a slide. Okay, so we have R3 and R4 is 120 and 60, and in parallel, we're going to take our Tandy Dandy TI-30X2S, we're going to put in 120 x minus 1 plus 60 x minus 1 is equal to, x minus 1 is equal to 40 ohm total. So Now we're going to put in 40 ohms is our total resistance for that parallel branch. Now you can now see that if we take this and we knock everything off to the right, we can see that's a series circuit. So very simply we can create a series equivalent for R2 through 5, and its resistance, we just add this up, 50, 40, and 10. I like that, 100 ohms. And that's in parallel with our first resistor, R1. And so we know that we have, is that 10 ohms? 100 ohms. 100 ohms in parallel with 100 ohms. And, you know, I'm a little slow, but if you have two exactly the same, you divide it by the total. So RT is 50 ohms, right? Our ET was 24? 24 volts. Okay, ET is 24 volts. So our IT is 24 divided by 50, not quite 0.5, but 0.480, right? Okay, so 480 milliamps. So now we're going to start going back. Now we had this right here, and that was talking about our total thing, right? Our equivalent parallel resistance, right? So what are we going to take down to here? We're going to take the voltage because we're going back to a parallel branch. So we're going to plug in our 24 volts. And we're going to plug in R234 is getting 24 volts for that whole circuit also, or that whole branch, right? So 24 divided by 100, we're just going to move the decimal place one place to the left or two place. Okay, so I1 is 0.0024. Is that correct? Anybody? Did I go too many? 1, 2. Oh, right, that's right. That's right. Okay. 0.24. 0.024. Oh, it's 0.24. You're right. Sorry. I'm going to get rid of that. Damn it. Bless you. And what do we have here? We had, I can't remember what we had over here. We had, oh, that was, okay, so we need a current. 2 through 5, right? Okay, so 24 divided by 100, 0.24. Well, that's the same exact thing. Amazing, I tell you. 0.24, 240 milliamps. Okay, now the next simplification we went back to, we've got everything else solved except this branch right here, right? Is that correct? And that's a series branch. 2 through 4, 2 through 5, 2, 3, 4, 5, because 3, 4 is being considered single, right? So we're going to take the series equivalent. What are we going to take in series? Current. So we're going to plug in 0.24. And then I5 is equal to 0.24. Then we're going to multiply up. And in this resistor, we're going to have, let me change colors here. So E5, we're going to have 2.4 volts. And up here, 50 times 0.24, 12 volts. So E2 voltage drop across resistor 2. And then our voltage drop, the one we really want to know is our voltage drop across R34 is 0.24 times 40. Say again? Thank you. 9.2 volts. Now, say again? Oh, that's totally different from 9.2. 9.6 volts. Okay. Now, from our original plan, let's go back and look at that. We had a parallel set right there, right? 2, 3 is in parallel. Am I looking at the wrong problem? Yeah, no kidding. All right. So here we have 3, 4, and we want to go back and look at our final analysis, and we're looking at this whole set right here for 3, 4, right? And that simplification back here, this part is in parallel. So what are we going to take from this right here? It's parallel, so we're going to take our voltage. Let's go back there and put in 9.6 volts. Wrong slide. Here we go. Okay, now we're going to divide that by 60 first and get our current. That's 160 milliamps. Now, if we divide 9.6 by 120, okay. Okay. We'll hit clear a couple times and then put in 9.6 divided by 120, enter, and then you should probably come up with about 0.08. What do you think? What do you find? Amazing, I tell you. So now we have solved everything in this circuit. Every single possible thing we've solved. Tell you how easy that is? All right. That's it for this slide presentation. And let's stop our recorder.